Okay, let's move on now to Ampere's law, which is basically the magnetic equivalent of Gauss's law, in that it relates the sources of magnetic fields, in this case currents, to the magnetic fields that are created in a more general way and an easier to use way than the Biot-savart law that we just discussed. All right, so let's take a look at Ampere's law. Ampere's law in the integral form is how we're going to start. Looks like this. We're going to start by defining some kind of a surface, and the surface has an outer loop around it, a path that encloses that surface. This is not a volume, it's just a surface with a path around the outside. And anywhere along this surface, we're going to have a little vector, anywhere along the edge of the surface, we're going to have a small vector dl that basically points along that path. So anywhere we go, we can draw a little vector dl that points wherever the path is going. All right, and then along this path, there may also be magnetic fields everywhere. So at each of these locations, we could define a magnetic field H, right? H is a magnetic field. In units of amps per meter. And we also know that it's related to the magnetic flux density via the permeability mu. So at any location, we know what the magnetic field is. And it may not be the same. It could well be varying in different locations. But what Ampere's law tells us is that if we take a loop integral around this entire loop, and I'm going to put a circle right here to indicate that it's a loop integral, and I'll put a C right here since it's a path. And as we do that loop, we're going to take the magnetic field and we're going to take the dot product of this little path vector dl. And if we walk around this path and sum up all those little contributions of h dot dl, or the component of the magnetic field that's in the direction of the path, if we do that, that's going to be equal to the total current that is enclosed, right? So we're going to add up all of the little bits of current that's inside of this area and add all that up, and that total current is going to equal to I. The better way to write this is as the integral of the current density J dotted with the small ds vector. In this case, we're going to have small vectors ds. The ds vector is going to point into the page as I've drawn it. And at this little box, there's going to be a vector j that's known, the current density. And we're going to take the dot product of that with ds and sum up all those little contributions so that only the component of the current density that is through the surface is going to contribute to this right side, right? So this is only the current that's through. Any current density that is along the surface is basically not going to contribute to this integral because the j dot ds is zero. Only the j term that is parallel to ds is going to contribute. Now, as I've drawn it, ds is into the board. And the way I know this is that you're going to apply the right-hand rule, that if you take your right hand and sort of spin your fingers around in the direction of the loop that you're taking, your thumb is going to point where the ds vector is. And so the ds vector is into the board. I couldn't draw it very well, but it is into the board. And that right-hand sense is going to hold up as we transition from the integral form to the differential form, which is the more powerful one. All right. I'm going to show you one example of the way we can use Ampere's law to figure out a magnetic field. And let's say we have an infinite sheet of current. Right. So I'm going to draw basically a piece of a plane, but this sort of extends infinitely far in all directions. I'm going to just try to indicate that with these little dashed lines. And along this entire surface, there's going to be a current, right? It's going to be Js. Js is a surface current. it has units of amps per meter, right? It's amps per meter because basically if I take a little 1 meter segment right there, and I ask the question, how much current is crossing through that, then I would take the JS, the surface current density, right? This is the surface current density, and I multiply it by that 1 meter, and now I have the number of currents, the number of amps that are passing through. So the surface current density is amps per meter. So what's the magnetic field from this sheet current? To figure that out, you can set up what's called an Amperian pillbox or something, which I don't have to worry too much about what it is, but it's basically a square that goes in and out of this sheet and is straddling both sides. And if you basically apply Ampere's law to that square, then you end up with the following, that H equals plus or minus JS, and let me just define coordinates here. Let's say this is the X direction. This is the Y direction. I shouldn't have to draw the Z at this point because you know X cross Y equals Z, but I'll just draw it. In this case, it turns out to be up. H turns out to be plus or minus JS over 2 in the Y direction. All right. Now that's kind of weird. So let's examine this for a second. First of all, why is there a plus or minus? It's positive or negative on opposite sides of the boundary. It goes in the positive Y direction on one side and in the negative Y direction on the other. The other thing is that it's in the Y direction, which should make sense if you imagine a point right here, right, that it's below the sheet, right? The contributions of all the current should be in the direction of J cross R. So J is in the positive Y direction, and the R vector is in the minus Z direction. So the magnetic field should be in the direction of J cross R. J is in the positive X direction, and we cross that with the minus Z direction. X cross minus Z equals in the positive Y direction. So we expect the magnetic field right here to be in the positive Y direction, like this. Above the sheet current right here, right? If I pick out a point right here, and this is now above the sheet current, and here's basically our R vector, then J cross R will be in the direction of positive Y crossed with positive Z, which equals, wait, I'm sorry, that's not a positive Y, that's a positive X. All right, positive X crossed with positive Z, which is minus Y. So we would expect a current that is in the, a magnetic field that's in the minus Y direction here, right? So this should be the magnetic field H that is set up on this side, right? So basically, if the sheet is, hang on, let me take a piece of paper. If the sheet's right here, all right, and I've got current which is going this way along the sheet, then the magnetic field will basically be pointed in and out perpendicular to the current, but parallel to or along the sheet. It's going to be in one direction on one side of the sheet, and if you go to the other side, it's going in the opposite direction as well. And you can always use the right-hand rule or current crossed with distance vector to figure out what direction the magnetic field is. The details of how you use Ampere's law to figure this out are in the notes, but the important thing that I want you to spot is that there is a duality between the magnetic field from a sheet current versus the electric field from a sheet of charge, right? Where if I had charges like this, it turns out that the D field equaled to plus or minus surface charge divided by 2. And it would be in the Z direction, right? Because the field lines in this case were flowing away from all these positive charges. So pointed upwards or downwards, depending on whether you were above or below. And the amount of that electric flux density was equal to rho s divided by 2. Right? It's the surface charge density divided by 2. For magnetic fields, it's Js, the surface current density, divided by 2, gives us the magnetic field. Now, there's a little bit of a break in the duality here, because the D is the electric flux density. And for magnetic fields, the equivalent is B, the magnetic flux density. But here we have an H, not a B. So this is a bit of a break in the duality, but still it's pretty good. And this concept, by the way, is going to help us understand magnetic boundary conditions as well. Right? Because basically the difference in the magnetic field from one side to the other, right? The delta H is going to be equal to Js from one side of this sheet to the other. And that should look pretty similar to the delta D equals rho s that we saw before. All right. Now in the notes, I have a few more examples of the ways in which you can use Ampere's law to solve magnetic fields. This is another one of those cases where in your basic physics classes, you probably learn how to set up and solve double or triple integrals. And in the real world, that's simply not practical. It's simply not done. There's a small number of cases for which there exists sufficient symmetry to do this, and you could find them in most every physics textbooks. Rather than make you do that in homework problems, they are all in the notes. So please take a look at this page in the notes, and you can see 4 different examples of magnetic field solutions that you can derive with Ampere's law. But again, the ways in which you set up and solve triple integrals is just not important here. All right. The other example that I have in the notes is applying Ampere's law to a wire that has sort of a uniform current density within it, or a current density that varies as a function of radius, and how you figure out what the magnetic field is inside that wire. So here's a wire. And you've got a current here that is a function of the radius, and how do you figure out the magnetic field inside that wire? You can solve that with Ampere's law, and if you want to see the specifics, it's in the notes. The other thing that I want to point out to is there is more detail about the current sheet and the charge sheet, and I'm going to call that up real quickly and show you. Yeah, so here is showing the duality between sheet of current and sheet of charge, which are basically the same thing, just electric fields and magnetic fields. And there's really a fascinating symmetry between the two in the way that we're applying Ampere's law versus Gauss's law. We set up a cube versus a square. You solve all the pieces, and you end up with a plus or minus Js or plus or minus rho s for the current and charge, respectively. And again, take a look at the details. They're all right there. All right. So that concludes section 2 on Ampere's law. In the next section, we'll briefly talk about permeability, or the way in which magnetic materials respond to magnetic fields.